In the previous video, we have introduced some fundamental definitions and basic concepts for vehicle motion planning. In this video, we will now turn our attention to important methods and algorithms that can be used for vehicle motion planning. Before we start, it should be mentioned that the field of methods and algorithms for vehicle motion planning is truly vast. It would require at least an entire dedicated course to somehow cover this topic appropriately. Hence, in this video, we will only be able to look at the most important concepts and scratch a little bit on the surface. Let's get started with the concept of a vehicle motion primitive, or simply a motion primitive. In fact, a motion primitive is a pre-computed, possibly parameterized motion, meaning a path or trajectory that the vehicle can execute. This means that the motion primitive satisfies or can be made to satisfy the kinematic and the dynamic constraints of the vehicle. Important examples of motion primitives are straight lines and circular arcs, meaning fractions of a circle. Note that in order to satisfy the kinematic constraints of the vehicle, these circular arcs must have a minimum radius, which is related to the maximum steering angle of the vehicle and the wheelbase. The combination of these particular motion primitives leads to so-called Dubin's paths, which are named after the American mathematician Lester Dubins. He published a seminal paper in 1957 with the title "On Curves of Minimal Length with a Constraint on Average Curvature and with Prescribed Initial and Terminal Positions and Tangents." In this paper, he provides a mathematical proof that the shortest distance between any two given configurations using the kinematic bicycle model consists of at most three motion primitives, which are given by straight lines and circular arcs of the minimal possible radius. Here we see examples of Dubin's paths in three specific scenarios. In each scenario, the given starting configuration of the vehicle, meaning its position and orientation, are indicated with the red arrow. The target configuration, which is the configuration we want to move the vehicle into, is given with a green arrow. The yellow lines indicate the respective Dubin's paths, which move the vehicle from the starting configuration into the target configuration with the minimal possible distance. The white dashed circles correspond to the minimum turning radius of the vehicle. Observe that in each scenario, the Dubin's path is given as a combination of exactly three motion primitives. In the first scenario of a left turning arc, then a straight line, and then again a left turning arc. In the second case of a left turning arc, followed by a right turning arc, and then again a left turning arc. And in the third case, a left turning arc, followed by a straight line, followed by a right turning arc. The approach of Dubins has been extended by the two mathematicians James Reeds and Lawrence Shepp in 1990 in a paper with the title "Optimal Paths for a Car that Goes Both Forwards and Backwards" to what is called Reeds-Shepp paths. As opposed to Dubin's paths, where the vehicle can only move forwards, Reeds and Shepp consider a kinematic bicycle model that can move both forwards and backwards. They provide a mathematical proof that the minimum length path, called the Reeds-Shepp path, between two given vehicle configurations, when the vehicle can move forwards and backwards, consists of at most six motion primitives, meaning, as before, straight lines and circular arcs. Moreover, they show that in total, there exist only 48 possible combinations of these at most six motion primitives. Again, let's look at examples of two specific scenarios where we want the vehicle to move from an initial configuration shown with a red arrow to a target configuration shown with a green arrow. As before, the white dashed circles indicate a turning maneuver of the vehicle with the minimum possible radius. The yellow lines now indicate the corresponding Reed-Shep path. Observe that in the first scenario, the Reed-Shep path consists of 4 motion primitives, namely a forward left turn, followed by a forward straight line, followed by a forward left turn, and finally a backwards right turn. In the second scenario, the Reed-Shep path consists of 3 motion primitives, namely a forward left turn, followed by a forward right turn, followed by a backwards left turn. Now let's add a couple of remarks for these 2 methods. First, both Dubin's paths and Reed-Shep paths assume the absence of obstacles. This means that the way these paths are constructed and their minimum length property are only valid in environments without obstacles. It does not mean we cannot construct the same type of paths consisting of straight lines and arcs as motion primitives also for planning problems with obstacles. However, this is an extension of the original work of Dubin's and Reed and Shep and has been considered by many authors ever since. Second, it's obvious that Dubin's paths and Reed-Shep paths produce steering profiles that are discontinuous. In fact, the steering angle constantly jumps between the maximum left steering, the maximum right steering, and the 0 value. For instance, for the first scenario on the slide, the steering angle jumps between the maximum steering angle to the left, then a 0 steering angle, then again a maximum steering angle to the left, and then we have a jump to the maximum steering angle to the right. In the second scenario, we have the maximum steering angle to the left, then the steering angle jumps to the maximum steering angle to the right, and then again the maximum steering angle to the left. In practice, this causes at least 2 problems. 1, following these paths requires a lot of steering efforts, and the steering profile does not seem very intuitive for the passengers. And 2, since changing the steering angle always takes a little bit of time, we have to stop the vehicle at each of these transition points, here, here, and here, in order to change the steering angle between the discontinuous values. Again, a lot of modern research has explored possible extensions to the original Dubin's path and the original Reed-Shep path in order to get rid of this problem of discontinuous steering profiles. And the final remark is about why we consider Dubin's paths and Reed-Shep paths in this video. On the one hand, they are of course milestones in the field of path planning for vehicles. But on the other hand, the basic idea of concatenating motion primitives carries over to many motion planning algorithms that we will consider in the following. Hence, understanding the way that Dubin's paths and Reed-Shep paths are constructed is helpful for understanding the basic algorithms that we will discuss in the following. Let's start with the most important criteria that motion planning algorithms generally aim to optimize. First, energy or fuel consumption of the vehicle. Second, travel time or progress made along the road. And third, passenger comfort, which is of course not easy to measure, but it's usually put into some relationship with the acceleration or the jerk of the vehicle, either in lateral or longitudinal direction. The term jerk refers to the derivative of the acceleration with respect to time. So, in summary, a general motion planning algorithm aims to compute a path or trajectory that optimizes one of these 3 criteria, or a combination of these criteria, or maybe even a different criterion, subject to a bunch of constraints including the kinematic constraints of the vehicle, the dynamic constraints, and obstacle avoidance. Now, let's continue with a rough classification of motion planning algorithms, which is particularly important since it's impossible to give an exhaustive list of algorithms, and especially it's impossible to do that as part of this course. First, we can distinguish between goal-oriented and progress-oriented motion planning algorithms. Goal-oriented motion planning algorithms aim to bring the vehicle to a specific goal configuration, for instance, a parking lot. For example, an algorithm for computing Dubin's paths or Ricci paths falls into this category. Progress-oriented motion planning algorithms, on the other hand, do not aim to bring the vehicle into a specific goal configuration, but rather they simply aim at making progress along the road. Imagine, for instance, driving along a highway where you do not want to be in a particular position after, let's say, 5 seconds, but rather you just want to move along the road as good as possible. Furthermore, motion planning algorithms can, more or less, be assigned to one of the following 3 classes. The first class is called variational methods, which are also known as curve-fitting methods. The main idea of these algorithms is to express a path or trajectory as a parameterized curve, such as a sigmoid function, a clothoid, a polynomial, or a spline. The parameters of these curves are then chosen to satisfy all the relevant constraints, including the kinematic constraints of the vehicle, the dynamic constraints, and collision avoidance, and otherwise to optimize the parameters such that the shape becomes optimal with respect to the chosen criterion, which can be one of the ones that we have discussed before, so minimizing energy or fuel consumption, minimizing travel time, or maximizing passenger comfort. An important example of variational methods is the so-called trajectory optimization, where the trajectory planning problem is formulated and solved as a numerical optimization problem. The second class of vehicle motion planning methods is called incremental exploration methods, which are also known as sampling-based methods. Here, the idea is to start from the current vehicle position or configuration and then gradually construct a reachability graph based on motion primitives. In these methods, the exploration of new points or configurations is usually based on random sampling, which is why they're also called sampling-based methods, and it is typically guided by a heuristic function. This means that in each step of the algorithm, a new point or configuration is sampled at random, and then it is tried to be connected to existing nodes of the graph using a motion primitive. And guidance by a heuristic function means that the random new point or configuration is not sampled according to a uniform distribution, but rather points and configurations are sampled with a higher probability, which are deemed as more likely to lead the vehicle to its target configuration. An important example of incremental exploration methods is the rapidly exploring random tree, or RRT for short, which we will look at in more detail later in this video. The third class of vehicle motion planning methods is called graph search methods. Here, the idea is to discretize the search space or configuration space into a grid of cells, and then associate each cell of this grid with the nodes of a graph. Two nodes are connected with an edge of the graph if there exists a collision-free motion primitive between the corresponding cells. Then we can apply any classical graph search algorithm, such as Dijkstra's algorithm or the A-star algorithm, to search the graph for the best path that transitions from the current vehicle node to a given target node. Now let's look at some examples in order to illustrate each of these classes of motion planning methods. The first method we look at is called path planning using polynomials, and it comes from the class of variational methods. The basic setting is that we have a vehicle driving on a road, possibly with multiple lanes, and we're trying to plan a path for this vehicle. To this end, we consider a bunch of polynomials in the vehicle coordinate frame. Typical degrees chosen for these polynomials are 4, 5, or 6. In our case, we have selected the polynomial to be of degree 5. The task of the motion planning method is now to find good values for the polynomial coefficients C0 through C5. Of course, the selection of the coefficients must be such that all relevant constraints are satisfied, including the kinematic constraints, the dynamic constraints, and the collision avoidance constraints. On top of that, we probably have an optimization criterion here that is related to the vehicle following its current lane as good as possible. Since here, the aim is not to bring the vehicle to a specific goal state, this is clearly an example of a progress-oriented motion planning method. A simple algorithm could simply look at a lot of combinations of polynomial coefficients C0 through C5. These combinations then lead to a large number of candidate paths, much larger than the 6 exemplary paths that are shown in this image. The algorithm may then simply evaluate each of these paths with respect to constraint satisfaction and select the best one according to the objective criterion. The second motion planning algorithm that we will look at in more detail is the rapidly exploring random tree, or RRT for short. If you have seen the RRT algorithm before, maybe as part of another robotics class, you may realize that we are using a different version here, which accounts for the non-holonomic constraints of the vehicle. Before we dive into the details of the algorithm, it should be said that the RRT belongs to the class of incremental exploration methods, and here we use the RRT for goal-oriented motion planning. The basic setup is as follows. Suppose we want to bring the vehicle from an initial configuration, meaning position and orientation, to a given goal configuration, meaning again position and orientation. The path that shall be computed between the starting configuration and the goal configuration shall be a continuous concatenation of straight lines and arcs of a given minimum radius in order to satisfy the non-holonomic constraints of the vehicle. This may remind you of the Dubin's path, since we're using the same type of motion primitives here. However, the major difference is that we consider map limits and also obstacles in the way. Now, the RRT algorithm works as follows. It starts with a single node that corresponds to the initial configuration of the vehicle. Then, it incrementally constructs a reachability graph starting from this initial node. For illustration purposes, suppose we are already in the middle of the algorithm where we already have a reachability graph consisting of 3 nodes which are connected by these 3 motion primitives here. Now, in each step of the algorithm, we randomly generate the planar coordinates of a new node, for example this one here. Then we tentatively connect the new node to some or all of the existing nodes of the reachability graph using a motion primitive, so in this case using either circular arcs or a straight line. In our example, we tentatively connect the new node to all 3 existing nodes of the reachability graph using the arcs shown with dashed yellow lines here. What's important is that the connection of the new arcs to the reachability graph in the existing nodes, such as for example here, is not only such that the path is continuous in terms of the x and y coordinates, but also the orientation should be continuous. This is needed in order for the resulting path to satisfy the non-holonomic constraints of the vehicle. Note that, geometrically speaking, an arc is uniquely defined by 2 points and a given orientation at one of these points. The next step of the algorithm is to check each of the tentative connections for constraint satisfaction, that is, whether they satisfy the required kinematic and dynamic constraints of the vehicle and whether they are collision-free. In our example, this arc here is certainly not collision-free because it overlaps with this obstacle here. So this arc would be removed by the algorithm. And then we have this arc here, whose radius may be smaller than the minimum turning radius of the vehicle. So in this case, this connection would be removed because of the kinematic constraints of the vehicle. Clearly, for step 4, we need functions that automatically check for constraint satisfaction of a motion primitive. In particular, we need a function for collision checking. Collision checking is a whole new topic in itself, and we will not deal with this in any more detail at this point. Now, in our example, there's only one feasible motion primitive left that connects the new node to the existing reachability graph, meaning only one motion primitive which satisfies all of the constraints. If there were multiple feasible connections left, the next step of the algorithm would select the best one, meaning the one that optimizes the given planning criterion, for example, the minimum length of the path. Then we add the new node and the best connection to the reachability graph, and we proceed with step 2 again. In case we cannot find any feasible connection, we simply discard the new node and go back to step 2 and generate a new random node. The RRT algorithm runs this whole loop, meaning steps 2 through 5, until a termination condition is satisfied. So for instance, until we have reached a maximum number of iterations, or until we have found a valid path from the starting node to the final node. Clearly, there are several details of this algorithm that have not been specified or that can easily be changed. This means that this algorithm is really a whole family of algorithms. For example, we have not specified according to what distribution this new node here is generated. We probably want to sample nodes which lie on the direct connection between the starting configuration and the goal configuration, with a higher probability than nodes, for instance, that are in some other corner of the map. Also, we want to sample the goal position as a new node with some probability in each step of the algorithm. The third and final method for motion planning that we look at as part of this lecture is the Dijkstra/A* algorithm, which are actually two different algorithms that are very closely related. Unsurprisingly, they belong to the third category of motion planning algorithms, namely graph search methods, and here we're using them for goal-oriented motion planning. More specifically, the algorithms are used to find the shortest path in a classical graph between a starting node and a goal node. You should imagine this graph in a similar way to the reachability graph of the RRT algorithm, meaning that the nodes represent vehicle configurations and the edges represent motion primitives that allow the vehicle to transition between the nodes in a way that all the relevant constraints are respected, meaning the kinematic constraints, the dynamic constraints, and also the motion primitive should be collision-free. However, for simplicity of representation, we show the graph here as a classical graph where the nodes are represented by little circles and the edges are represented by straight lines, which does not mean that the physical path between two nodes is actually a straight line, but the presence of an edge just means that there exists some feasible motion primitive that connects these two nodes. Hence, we refer to the edges as logical connections instead of physical connections between the nodes. The main difference between this graph and the reachability graph of the RRT algorithm is that this graph is not incrementally constructed by sampling new random nodes, but this graph is fully deterministic and fixed from the beginning of the algorithm. Of course, this deterministic graph has to contain an initial node and a goal node corresponding to the starting configuration and the goal configuration of the vehicle. For convenience, we assume that the nodes of the graph are numbered. In the case of our little example graph here, we have 6 nodes, so each node receives a unique number from 1 to 6. Furthermore, the Dijkstra and A-star algorithms work on a weighted graph, which means that each of the edges of the graph carries a number called the weight of this edge. This number is related to the relevant optimality criterion, for example, the travel time, the travel distance, or the fuel consumption, which is considered as a cost for the vehicle to move along the motion primitive that corresponds to this particular edge of the graph. So in summary, the goal of the algorithm is to find an optimal path through the graph from the initial node to the goal node, such that the sum of the weights of the edges that are traveled along by the vehicle is minimized. To this end, the Dijkstra algorithm works as follows. The first step is to set up the so-called optimal policy table. It is shown down here for our little example graph. It is a table with 4 columns. The first column contains a list of all the nodes of the graph. The second column indicates the prior node according to the optimal policy. The third column indicates the tentative cost from the initial node, and the fourth column indicates whether the node has been visited. The meaning of these columns will become more clear when we go through the details of the algorithm. The initial setup of the table is as follows. The initial node has no prior node, and its tentative cost to go to the initial node is 0. All other nodes have a tentative cost of infinity, and none of the nodes has been visited. Now the Dijkstra algorithm repeats the following steps in order to incrementally fill or amend the optimal policy table. The first step is to pick the non-visited node with the lowest tentative cost. In our example on the left, this is the initial node. Then, for all neighboring nodes of the selected node n, calculate the tentative cost of going to the initial node through n. In the case of our example, this means the following. Recall that the selected node n here is the initial node, and the neighboring nodes are the nodes 2, 3, and 4. Now, in order to calculate their tentative cost of going to the initial node through n, we have to add the tentative cost of n, which is 0 in this case, to the weight of the respective edge that connects the nodes 2, 3, and 4 to the node n, so in this case 7, 14, and 9. Now, if the calculated tentative cost is lower than the existing tentative cost, then we have to update the optimal policy table accordingly. In our example, for node 2, the calculated tentative cost is 7 and the existing tentative cost is infinity, so we update the tentative cost to 7 and the prior node becomes node 1. For node 3, we have the calculated tentative cost of 14, which is again lower than infinity, so we update the tentative cost to 14 and the prior node becomes 1. Similarly, for node 4, we get a new tentative cost of 9 and the prior node again becomes 1. The final step is to mark the node n as visited, which we do with a green check mark in our table, and go back to step 2. The next non-visited node with the lowest tentative cost is node 2 because 7 is less than 14 and 9. Its neighboring nodes are 1, 4 and 5, of which we only have to consider 4 and 5 because 1 has already been visited. Calculating the tentative cost to the initial node through node 2 yields 7 plus 10 for node 4 and 7 plus 15 for node 5. Now clearly 17 is greater than 9, so we do not have to update node 4, but 22 is less than infinity, so we update node 5 such that the tentative cost becomes 22 and the prior node becomes node 2. And finally, we mark node 2 as visited and we go back to step 2. The next non-visited node with the lowest tentative cost is node 4. Its neighboring nodes are 1, 2, 3, and 5, of which we do not have to consider nodes 1 and 2 because they have already been visited. For node 3, the calculated tentative cost becomes 9 plus 2, and for node 5, it becomes 9 plus 11. Since 11 is less than 14, we update node 3 in terms of its tentative cost to 11 and in terms of its prior node to 4. And since 20 is also less than 22, we update node 5 in terms of its tentative cost to 20 and in terms of its prior node to 4. Finally, we mark node 4 as visited and we go back again to step 2. The next non-visited node with the lowest tentative cost is node 3. The only non-visited neighbor node of 3 is node 6, and the calculated tentative cost becomes 11 plus 9, so 20. Clearly, 20 is less than infinity, so we update node 6 with a tentative cost of 20 and the prior node 3. And finally, we mark node 3 as visited. Next, we have two unvisited nodes left, which both have the lowest tentative cost of 20. So we pick one of them at random, let's say for example node 5. The only unvisited neighbor of node 5 is node 6, for which the calculated tentative cost becomes 20 plus 6, which is of course larger than 20, so we do not have to update node 6. Then we mark node 5 as visited and we proceed again to step 2. Now we only have one node left, which is node 6, so any considerations for node 6 will not change the optimal policy table and we are done. In general terms of the algorithm, this means that it terminates when all the nodes are visited, like in our example here, or alternatively, all nodes which are unvisited have the tentative cost infinity. Now our final question is, how is this optimal policy table related to the shortest path between the initial node and the goal node, which is what we're actually looking for? And the answer is that we can easily construct the shortest path from the optimal policy table in the following way. We start with the goal node and then we go back to the prior node, which is node 3. Then from node 3, we go back to the prior node, which is node 4. And then from node 4, we go back to the prior node 1. And this gives us the shortest path in the given graph from the initial node to the goal node. Now, two final remarks about this approach. First, if you look at a lot of textbooks and scientific literature, the Dijkstra algorithm is often formulated backwards, meaning from the goal node to the initial node, instead of from the initial node to the goal node like we did it. In fact, these two formulations are more or less equivalent. And second, the A-star algorithm is actually very similar to the Dijkstra algorithm. The only difference is that the A-star algorithm includes an additional heuristic function that underestimates the distance of each node to the goal node. This heuristic function is used to make the algorithm more efficient in cases where there's also a spatial structure behind the logical graph, which is the case for our motion planning problem, because as you may remember, each node of the graph corresponds to a position in a spatial map.